Center. Stephanie, are you there?
Yes, I'm here. Okay, I can go ahead and get started then. Good morning, everyone. Thank you for the introduction. As you mentioned, I'll be talking about the generation and application of payload thermal environments for a lunar lander mission. More specifically, I will go over a little bit of background, why there is a need for the generation of thermal environments, what thermal environment data is required, how to generate that data from the vehicle perspective, and how to apply it from the payload perspective. And I'll briefly talk about some advantages and disadvantages of this method as well. So the work that I will be presenting on came from working on the Lunar Catalyst project, and the example that I show uses the Astrobotic Peregrine lander. The current lander image from their website is shown in the top right image here. And Lunar Catalyst was a NASA project that ended last year that helped competitively selected commercial companies develop lunar lander capabilities that could lead to future robotic lunar lander missions. And overall, the hopes of Lunar Catalyst was to help develop lunar landers that could be integrated with U.S. commercial launch capabilities to deliver payloads to the lunar surface. And my work on that project was working as the thermal engineer for Astrobotic's lander. And I presented last year at TFAWS on the challenges of designing a passive thermal control system for the Astrobotic Peregrine lunar lander. The CLIPS program, Commercial Lunar Payload Services, is an ongoing NASA program that supports the Artemis program. And it's kind of like the next step after Catalyst because CLIPS contracts transportation services to send NASA payloads to the moon. And in May of last year, NASA awarded contracts to Astrobotic and 2 other commercial companies to be moon landing service providers under this program, which means that these companies would be flying NASA-developed payloads on their commercially developed landers. And today in the space industry, there's a lot of partnerships between government agencies, commercial companies, universities, and other entities. So one organization may be developing a payload or an instrument that rides on a vehicle developed elsewhere. For example, a NASA CLIPS payload riding on a lander built by a commercial company. So this can create a bit of a challenge for the payload engineers in determining their environments. The thermal environments of space, Earth orbit, lunar orbit, and the lunar surface are relatively well known, but the thermal environment of the payload flying on or within a vehicle would need to take into account the impact of the vehicle on the thermal environment. The thermal impact from the vehicle is influenced by a number of different things, including the mounting location on the vehicle, the temperature of that mounting location, the mounting method, if the payload views the sun or is shaded, proximity to other payloads and components, mission phases, such as if the vehicle turns and changes the payload's view to the sun, and of course, other aspects you may not know, just not being as familiar with the vehicle. So in this method of generating environments that I'm going to talk about can be used in other applications as well. For example, it could be for generating environments for a component within a system that you're creating a more detailed model of, but I'm going to use the payload and vehicle example to describe this. So to have a full picture of the surrounding thermal environment, a payload would need to know the mounting location temperature, the required thermal isolation to the mount location, or the mounting method. I say required thermal isolation because often a vehicle provides the payload with a requirement defining how thermally coupled to the vehicle that they can be. You'd also need a sink temperature with an associated thermal contact for each side of the payload, the total incident solar fluxes for each side of the payload, and the total incident infrared fluxes for each side of the payload. So how is this information generated? It can all be obtained using Thermal Desktop, and this is assuming that this information is being generated by the vehicle thermal engineer. So they have the vehicle system modeled in Thermal Desktop already. And as an example, I'm using the Astrobotic Peregrine Lunar Lander And if you're familiar with Astrobotic, you know that the design has evolved past this older version, but this is what I'm using as an example shown in the top image. So this work was done for unknown payloads for general locations. So the first step was to create representative payload geometry, and then the thermal effects on those representative payloads will be calculated. So at this point in the vehicle design, there were 4 decks. So the general locations that I used for the representative payloads were on the top and bottom of each deck, so that there are 8 total. And each representative payload is a simple 15-centimeter cube with 5 sides, not 6 sides because the side facing the mounting location doesn't need to be included. Each surface has 1 node and blackbody optical properties of an IR emissivity and solar absorptivity both equal to 1. The thermal physical properties and surface thickness don't matter of the representative payload, but if you wanted to calculate this data for a more specific payload, you could use more specific geometry, shape, and location for more accurate data. First, I'll explain how to generate the sink temperatures and corresponding radiative conductors, and this will calculate what overall temperature each side of the payload radiates to and what that radiative contact is. The T-Sync command in Thermal Desktop is used for this, and there are some short and informative sections about the T-Sync command in the Thermal Desktop and SINDA manuals, and I recommend reading those if you use this, if you haven't used this tool before, because they're very helpful. This data is calculated after the model is run with the representative payloads included. So once the model is run, you open the T-Sync calculator, which is shown in the left image, and select the save files that you want to calculate the data for. Then select the Add button on the right side of the edit box to add your data set. And in your data set, you will enter the nodes for which you want to calculate the sink temperatures. You can also enter any nodes you want to exclude from the calculation, which I did not need to do in this case. If you select to ignore connections of the T-Sync node list, you will exclude the effects from the other sides of the representative payloads, which is what we want in this case. Including the applied Q includes the solar albedo and Planetshine effects, which is also what we want in this case. And for this type, you can select either linear, radiation, or both. And in this case, it's only radiation. The manual also recommends that if you do need linear and radiation effects, that you calculate them separately and not use the both option, but that option exists. So this is an example of the T-Sync calculator with the filled-in options. I have 1 save file added here, but you can add multiple. And each data set is one of the representative payloads. So it has A top, A bottom, B top, B bottom, etc. So within one data set, there are 5 nodes for that payload, and the options are selected here that I just explained in the previous slide. And once your options are set and you tell it to calculate, Thermal Desktop generates an Excel file for you, which is output in the folder where you're running the model. The file includes the time, because this is transient data, the radiative conductor, and the sink temperature for each node that you selected. The units are included, which is nice here, and the conductor units are meters squared because it's a rad K, and the conductor doesn't actually change its time, it's just listed in the table for each time step. And this data is given for each node selected. So for calculation with 8 payloads with 5 sides each, this file includes this data for all 40 nodes. And they're labeled by the submodel ID and node number, so be sure to give your submodels informative names so that you know which node is which. So now that we know how to calculate the sink temps for each side, let's talk about the fluxes. If you remember a couple of slides ago, the optical properties of the representative payloads are blackbody properties. So the incident flux is equal to the absorbed flux. And we want to calculate the incident flux because what is absorbed by each of the actual payloads is going to also depend on their individual optical properties. So that is why blackbody properties were used, because in theory, the vehicle wouldn't necessarily know what optical properties each payload has. The total incident solar flux and the total incident IR flux need to be calculated separately so that the payload can use their solar absorptivity and IR emissivity to determine how much is absorbed of each. And the solar albedo and Planetshine contributions are dependent on the environmental parameters and not the vehicle itself. And the IR flux from the vehicle depends on the vehicle's geometry and temperatures, and that difference is going to play into how each is calculated. To calculate the solar albedo and Planetshine fluxes, you need to edit your radiation analysis parameters within the case set manager. And by default, the three are combined, and we want to uncheck that box so that each is output separately so that we can separate the solar from the IR effects. You don't necessarily have to output them as fluxes, but it's making more work for yourself later if you don't. One important thing to note is that this change needs to be made before you run your analysis case. So the T-sync calculations are made after you've already generated your save file, but this needs to be done before. And once you've made that change and run your case, the data is output to the HRA file, the heating array include file, which is automatically generated. There's a nice description of everything included in this file in the thermal desktop manual, which is shown in the images on the left. You don't need to be able to read that tiny text for the sake of this presentation. I just wanted to show that that explanation exists in the manual. And the image on the right is an example from one of the HRA files that I generated. And this shows the incident fluxes on node 2 of the representative payload on the bottom of deck B. The submodel is highlighted there. And it is separated into solar, albedo, and Planetshine. So if we hadn't unchecked that box to combine those three fluxes, this would show just one array with a sum of all three. And in that file, those three arrays are included for each node. So now how do we get the IR flux from the vehicle? We're going back to the T-sync calculator, but we're going to select different options. So you open the T-sync calculator and select your save files, just like I previously showed, but this time when a data set is added, you do not include the applied Q. And that is going to exclude the effects from solar albedo and Planetshine and only use the effects from the vehicle geometry to calculate the sync temp. And again, we're not calculating a single sync node, and the type is radiation. So this is calculating a sync temperature and not a flux. So additional calculations are needed. The output will be the same as the example file I previously showed, an Excel file with a sync temperature and a RAD-K conductor, and the data is used to determine the IR flux from the vehicle only because we excluded that solar albedo and Planetshine in the sync temp calculation. So the starting equation that I show here is from the Syndifluent manual, and it is how the sync temperature is calculated. And the sum term is the total absorbed heat, which, since we use black body properties, is the same as the incident. The QN times QI term is the applied Q, which we did not include. So unchecking that box to include the applied Q sets QM equal to 0. So that term is 0. And then the denominator is the RAD-K conductor multiplied by the Stefan-Boltzmann constant. So this equation can be rearranged to calculate the Q and the IR spectrum from the vehicle. And the sync temp and RAD-K contact are the values that we generated with the T-sync calculator. And then we also know that Stefan-Boltzmann constant is 5.67 times 10 to the negative 8. So this can be easily calculated. And then to convert it to a flux, we divide by the area for which we're calculating, which is also known because it is the side of the representative payload. And now you have the incident IR flux contribution from the vehicle. And I calculated this in an Excel spreadsheet. So I just copied the equation for each node and dragged it down to calculate for each time step. A few additional calculations are needed. The solar and albedo flux outputs are added together to calculate the total incident solar flux. And those were calculated at the same time intervals, so they can just be added at each time step. And then the Planetshine and IR from the vehicle are added together to calculate the total incident IR flux. But for the total IR calculation, the Planetshine values are output based on the time step defined for the environment, which is defined in the orbit manager. And if it's for an orbit, I believe the default is 1/12 of the orbit period. But then the IR from the vehicle is calculated based on the output interval that is defined in the case set manager. So if those two time steps don't align, you'll need to extrapolate one set of data for the time intervals of the other before they can be added together. But once those additions are made, that is the data that in theory would be generated by the vehicle to deliver to the payload. So once the payload has the data, they can calculate the absorbed values based on their outer optical properties. The rad-K conductor will be multiplied by the IR emissivity. The total incident solar flux will be multiplied by the solar absorptivity to get the total absorbed solar flux. The total incident IR flux will be multiplied by the IR emissivity to get the total absorbed IR flux. And then so that you just have one flux per side, you can add the total absorbed solar and the total absorbed IR to get the total absorbed flux overall. So to do all those calculations, again, I created an Excel spreadsheet to make it easier for myself. So now, how are these environments applied to a payload model? To show how these environments are applied, I'm using an example CLIPS payload, the neutron measurements at the lunar surface, and NLS instrument. And this example is now from the payload thermal engineer's perspective, assuming the payload model already exists. So first you need to determine which sides of your payload correspond to the size of the representative payload, since we calculated the environment data for each side separately. And the corresponding sides are shown in the image included on this slide. For each side of the payload, besides the mounting location, you'll create a boundary node, which will be the sink temp for each side, and a corresponding radiation conductor, which was also that rad-K value that we calculated. And you'll also create a heat flux for each side. That will be that total absorbed heat flux. For the side that is the mounting location, you'll create a boundary node, which will be the mounting location temperature. I didn't explain how to calculate this in the vehicle model because it's just the straightforward temperature structure at the mounting location. There will also need to be a thermal contact to that node, which may be a value dictated by the vehicle or may just depend on your mounting method. There's not a heat flux created for that side because it's not viewing anything to have a solar flux. So for each boundary node, you just copy the generated sink temperature versus time, which would have been provided. And I included enablers for each boundary node, which I will explain further in a couple of slides, but that is why that enabler is shown. For the conductor to the boundary node, again, use the same enabler, and you can define your conductor as a rad-K, which will be the generated conductor value multiplied by the outer emissivity. And the outer emissivity doesn't have to be a symbol here, but I've created a symbol for that to make any future changes easier, because you're creating these sink temperatures and conductors for 5 different sides. So if you change your outer emissivity later, that's going to save you time if you have it as a symbol. And one important thing to note is that if you've added MLI to the outer surfaces of your payload, you need to select insulation nodes so that the environments are applied to the outside of your insulation and not to just the outside surfaces of the payload, which would be inside the insulation. To apply heat fluxes, again, use that same enabler. And the time-dependent heat flux copied in here is the total absorbed. So as I previously explained, as the payload thermal engineer, you would take the total incident fluxes provided, multiply the total incident solar flux by the solar absorptivity, and multiply the total incident IR flux by the IR emissivity, and add the two together to get the total absorbed flux. And again, make sure that you put heat into insulation nodes. And here's where the enablers come in. If you are modeling a vehicle or payload for multiple mission phases, you'll want environmental data for each of those mission phases. So instead of creating multiple models, you can create multiple environments and turn them on and off in each case. So for 4 different mission phases, create 4 boundary nodes, conductors, and heat fluxes for each side of the payload, like I just showed. And each mission phase will have its own enabler symbol that will be either 0 or 1. And then within the case set manager, for each specific case, you'll set the symbol that corresponds to the phase being analyzed to 1, and then set the other symbols for the other phases to 0. There are a lot of advantages and disadvantages to this method. Some of the big advantages is that it enables partnerships between different entities working on different aspects of a project. And although I gave the example of applying the environment to a payload and thermal desktop, you could still use this data without thermal desktop. There are universities and smaller companies developing payloads that may not have a thermal desktop license. And even if you're just doing hand counts, you could look at the sync temps and fluxes at a certain time step and calculate a steady state build temperature of your payload. Another advantage of this method is that the system wouldn't have to provide a detailed model, so they wouldn't have to send huge files and can avoid sharing any possible proprietary data. There are also disadvantages, of course. One is that the data was generated for representative payloads, so it's not exact. And if this is for a system with lots of payloads mounted near each other, it doesn't include the effects from the other payloads if they're not in the system model. Additionally, for the payload analysis, the payload thermal engineer needs to manipulate the data that's based on the optical properties of the payload. And if that is something that you want to look at different possibilities for, you'll have to redo those calculations. I used Excel for data manipulation and made the emissivity and absorptivity variables in Excel that I could change. But even with doing that, you would need to update each flux and conductor and update the symbols used. And if you have to update the fluxes and conductors from multiple phases, it's not an insignificant amount of changes. And it's just creating more opportunity to forget to update something. So that is the main disadvantage from the payload engineer perspective. An additional consideration that I didn't talk about in this presentation is that if you're analyzing a case on a planet surface, such as the lunar surface, and you have the surface modeled as a thermal desktop surface, then the model isn't generating the Planetshine fluxes like I've shown. Instead, the Planetshine fluxes will be included in the IR flux calculation using the T-sync calculator, because that's calculating the flux from geometry, and in this case, the planet surface is geometry. That's not necessarily a disadvantage. It actually makes generating the environments a little bit easier because it takes out that additional step of summing up the incident IR fluxes. It's just something that you need to be aware of so that you don't open up your HRA file and wonder where the heck your Planetshine data is. Just a brief summary, thermal environments are essential for thermal analysis for obvious reasons. And if you're analyzing a payload or component that is part of a larger system, you need to include the environmental effects from that larger system. Important thermal data to have is the mounting location, temperature, and contact, the sync temp and associated thermal contact, total incident solar flux, and total incident IR flux. And the necessary data can be generated by the vehicle designers, all using thermal desktop, and some additional data manipulation is required by the payload thermal engineer. And I used Excel, but you could use MATLAB or, another program. And one thing that I learned using this too is that the T-sync references in thermal desktop and Cinefluent were really good references in the manual. And that concludes my presentation. So my contact info is on here if you think of questions later.